All right, well, we are coming up on 5 after the hour, so I think in the interest of everyone's time, we'll go ahead and get started here. Thanks, everyone, and good morning, good afternoon, maybe good evening for some of you, whatever it is. We appreciate you taking the time to join. I'm Ron Hawkins, SDSC's Director of Industry Relations, and I'm usually your host for these, but I'm also your guest speaker today, so for better or worse. And we're going to be talking about our Expanse supercomputer, our newest production supercomputer, and what we're doing with that to, or how we're leveraging that to benefit our industrial engagements. So we'll talk a bit about the system itself and some features, and then talk more about the industrial engagement aspect of that. If I can get my slides to change. Okay, this is our first SDSC Technology Forum event of 2021, and some of you may know these used to be a breakfast, a local breakfast event, and like many things, we've gone virtual and expect to stay virtual for the foreseeable future. But as I look at the registration list, I see there are folks who are able to attend who probably wouldn't have shown up for breakfast. So that's the hidden benefit of being virtual. So schedule for the rest of the year is still a little bit in flux, but we do have May scheduled. We're going to have our partner GigaIO, a local technology company, talking about their interconnect fabric for composable hardware systems, something highly relevant in today's increasingly heterogeneous computing landscape. For June, we are hoping to have someone come and talk about the Cloud Bank project, which is facilitating multi-cloud access for NSF-funded researchers, and has some potential commercial benefits as well. September, we're planning to have a presentation on our forthcoming Voyager supercomputer. And then we have a date for October. We're still firming up the speaker details, but we are hoping to have one of our industry partners present on work with UK Biobank and population scale genomics, and that partner is still clearing their presentation with their marketing and legal departments. So expect to be able to share that, share more details on that soon. So hope some of these are of interest. Please stay tuned to our events page on our website, and as well as emails that you may receive, and sign up. Hope to see you at some of these in the future. All right, well, again, looking at the registration list, I get the sense that most of the folks today are pretty familiar with SDSC, but just by way of setting the stage, I wanted to kind of recap our recent, or fairly recent lineup of supercomputers. If you want to go farther back than the most recent decade, we've got a really cool timeline of SDSC events from its inception in 1985, and I've referenced a link there, so you can go take a look at that and get the ancient history if you're interested. But sort of 10 years ago, we fielded the Gordon supercomputer. It started out as Flash Gordon, but the name was shortened up due to some copyright concerns. But Gordon kind of heralded the emerging trend in data-intensive computing, with about 16,000 cores and 340 teraflops, and fairly high on the top 500 list at that time. And a few years later, we brought in Comet, and we coined the term long tail of science to sort of describe very diverse science workloads, sort of rack scale workloads, and Comet was designed to serve that community with about 48,000 cores. We brought in GPUs, which were beginning to emerge for tasks such as molecular dynamics. And Comet came in about 2.5 petaflops. And we did a lot of work on Comet for a few years, and were rewarded for that with Expanse, which we put into production at the end of 2020. Continues that kind of support for that long tail of science with some enhancements and additional capability and capacity, but also brings in a number of innovations that address kind of the changing landscape of HPC, including things like composable computing, science gateways, cloud bursting, and I'll mention a few of those as we go along. About 93,000 x86 cores, went a little down in the GPU count, but way up in the capability in terms of the NVIDIA V100 GPUs over the previous generations, and about 5 petaflops. And these systems were all very similar in terms of budget, so you can certainly see the march of Moore's law along that timeline. And this year, as I mentioned, we have forthcoming the Voyager system, which was announced recently, and it's more of a emerging technology system. It's targeted at artificial and machine learning in science, and utilizing specialized training and inference processors from Intel, the Intel company Habana. So I'm not going to say too much about that today, because we want to entice you back in a few months to hear a more detailed talk on that. So hope you'll be there. So moving back to Expanse, a few highlights here. It's built on a scalable unit concept, which we'll say more about, and which has a lot of bearing on what we're doing with the industrial program. Again, it's targeted at a diverse base of science users. I've listed a few here: multi-messenger astronomy, genomics, various earth sciences, even social sciences. Bringing in a more capability for data handling and data movement with a 12 petabyte high performance Lustre storage system, 7 petabytes of Ceph storage for project type of storage, node local NVMe drives for low latency random access for data analytics types of operations, plenty of connectivity to high performance research and engineering networks that span the country and the globe. And new features like, again, as I said, composable systems, high throughput computing via the Open Science Grid, various science gateways, interactive computing with things like Jupyter Notebook and RStudio, and containerized computing and cloud bursting. And our technology partners for Expanse include Dell, our overall system integrator, AMD and Intel processors, NVIDIA GPUs, Mellanox, which is now part of NVIDIA for interconnect, and Aeon Computing for our storage systems. A little bit of an eye chart here, but just a bit more on the Expanse system architecture. So we have actually 14 of these We call them SSCUs, SSD Scalable Compute Units. And they're interconnected on a HDR InfiniBand spine and leaf network. And we've got the capability to add some additional scalable compute units, again, factors into our discussion today. And overall, well, we're showing 13 here. It's actually 14 with our industry rack that we'll talk about. 728 total standard compute nodes. As I said, about 93,000 total cores, 200 terabytes of memory. 52 GPU nodes with 4 NVIDIA V100 GPUs per node, so 208 total GPUs. We have 4 large memory nodes that have 2 terabytes of memory per node for those memory intensive codes. And as I said, the substantial Lustre parallel file system for high performance scratch storage and Ceph for object storage, and a total of 1.2 petabyte of node local NVMe. And one of the kind of side benefits of bringing Expanse in was we were able to go to a direct liquid cooled system. So we're able to make the necessary facilities modifications in our data center to support the direct liquid cooling, and that's with our data center fixed real estate footprint. That's super important going forward with these high density racks and our ability to continue to expand our compute capability. And we'll be implementing, I'm sure, many other systems with liquid cooling going forward. So we talked about this scalable unit concept, and kind of some of the key design drivers behind that. One was the anticipated job mix. So I talked about these. This sort of rack scale job in terms of the typical workload. And so we can support a bit over 7,000 x86 cores within one of these compute units with full bisection bandwidth HDR 100 InfiniBand for closely coupled computing. And of course, with each of the nodes having 128 cores and 256 gig of main memory, plus the node local NVMe, we've got a lot of capability per node for high throughput computing and node level parallel computing. And then, as mentioned, each of the compute units provides some GPUs, whereas in our previous system, Comet, we had GPU racks, which added heterogeneity. So we've gone to a system where we provide some x86 compute and some GPU compute on a per rack basis, which benefits our efficient system support. And as I mentioned, we have for interconnecting our scalable compute units, we have a spine and leaf network with HDR InfiniBand full rate on the spine. And we have a 3-to-1 oversubscription from each compute unit up to the level 2 switch. And so this scalable compute unit concept gives us some scale out capability, which we'll talk about in a few minutes. Wanted to quickly mention some of these other features. This slide shows Well, two things. One, it shows the Science Gateway support coupled to cloud bursting capability. So we have, we're showing here our Cypress Science Gateway, which was one of the science gateways we developed early on a few years ago. It's for phylogenetic computing, or tree of life, so to speak. And we've seen very heavy usage of Cypress all across the globe. It's been a main driver of the compute cycles consumed on our Comet system. And also, well, as you can see from the slide, we've gone to cloud bursting as well to provide that additional scale out or elasticity for to accommodate all these users. And this sort of shows you the cloud bursting architecture here that has been developed at SDSC. We've done a lot of in-house work on that, along with some with a code called Terraform from HashiCorp. And so you can see that Cypress can now task jobs or send jobs either to the compute on Expanse or out to the Amazon cloud. And so again, as we as the sort of landscape of HPC changes, and we have the capability to leverage these cloud architectures, we have that kind of advantage of the sort of seemingly infinite elasticity that can be provided by the major cloud providers. Another feature that we mentioned was the composable systems concept, and we have deployed on Expanse the Bright Cluster Manager, which brings it brings a lot of different capabilities for both static and dynamic system management. But one of the key ones is, and we're showing on this slide, is the ability to provision from a common pool of compute nodes a mix of conventional batch scheduled HPC nodes with a scheduler like Slurm, as well as nodes that are managed with Kubernetes, which is pretty much the emerging standard for container orchestration. And this gives us the capability to sort of mix and match modes of operation where we need either conventional HPC or containerized computing that's managed with Kubernetes and can be easily scaled out to the cloud. And so we have a number of different projects that will be taking advantage of this composable systems capability. Just showing one here real quickly, which is the WiFire fire weather monitoring and prediction system that was developed at SDSC. And it's hard to see in the chart here, but it uses a complex workflow for its various tasks. It's managed by the Kepler workflow management system. This project is led by Ilkay Altintas at SDSC, and she's really done a lot to take this system from an NSF-funded basic research to a system that's now used by various fire agencies around California and the US. But this workflow can take advantage now through the composable systems of both compute at HPC compute on Expanse at SDSC, containerized computing with Kubernetes, both on-premise as well as in the cloud. So it gives a lot of flexibility for these kind of systems that need a variety of high performance and computing capacity and near real-time computing to support things like response to fire events. So switching gears a little bit, just to mention briefly a little bit about our industrial engagement programs. We've always tried to keep a portfolio or a toolkit of programs that allow us to work with industry in different ways that are tailored to the needs of our industrial collaborators. And so we've got conventional sponsored research contracts, pretty much the bread and butter of university and industry engagements. We've got service agreements for the use of our computing and storage systems, and also providing expert consulting for things like code porting, code tuning, user support. We've developed industry-supported focused centers of interest over the years in areas like big data systems benchmarking and blockchain technology. We have our Advanced Technology Lab, which brings in new hardware and software technology for evaluation, benchmarking, and prototyping. And with that and the bringing our Voyager system online this year, expect a major focus on our Advanced Technology Lab on AI-related software and hardware technologies. And we'll have more to say about that over the course of the year. But in many cases, our industrial projects and collaborations have taken advantage of our supercomputer systems. And just a few examples here. We've worked with a number of different companies on whole human genome analysis, for pharmaceutical development, for healthcare technology. We've done benchmarking of life sciences codes, like for cryo-electron microscopy analysis. We've worked with civil engineering firms to do things like earthquake, finite element analysis for the Bay Area Rapid Transit System earthquake retrofit. Worked with in the defense area, doing high performance storage systems benchmarking. And with oil and gas companies for exploration data analysis and visualization. So we've always had that tie-in to leveraging our supercomputer systems, often bringing unique capabilities that can benefit these collaborations. And typically with the NSF-funded systems, we're limited to 10% of the system, what we call the director's discretionary portion of the system for our industrial collaborations. But with the development of Expanse and its scalable compute unit architecture, we recognize an opportunity there to bring in additional capabilities specifically to support our industrial projects. And so with a financing program from the university, we were able to purchase an additional or 14th scalable compute unit beyond those funded by the National Science Foundation, and dedicate that to our industrial program. And so we have purchased that system. It's been installed. We're bringing it online this month. And it provides about 62 million x86 core hours per year and 140,000 V100 GPU hours, specifically to support our industrial projects. So gives us a lot of capacity and capability that's under our complete control for work with our industrial partners. And we do we have multiple ways to provide access. We can do it directly with via service agreement, but we've also engaged with a third party to provide a portal-based system to facilitate industrial access. And that partnership was actually supposed to be announced earlier this week, but we're a little behind in our communications. So stay tuned for that. There's some press release and other communications coming out to talk more about that any day now. And I think that is all I have to say at the moment. I did want to mention and neglected to mention that we have Mahidar Tataneni with us today. He is SDSC's head of user support, and he's here to help me answer any technical questions you may have about the Xpanse system. And I very much appreciate him taking time out of his busy day to join us. But at this point, I would like to open the floor to questions.